Mohammed Saad.
So page 223.
Page number 223, huh? Okay. Okay, page 223 is here. What's the equation number? 12.5.
12.5.
Okay, so here is the dynamic strength of the gears. Okay, he has just altered the things. A dynamic tooth load he was specifying in case of an helical gear and a spur gear. Just there is a change of notation. That's it. Okay, so here he call it as Fs rather than Ft. So you can take this particular equation, which is in table in equation number 12.54, which is in the page number 223. Take that particular equation there. So I have just done that. So equation number 12.54, page number 223. From there you can pick this particular equation. For this, whatever you require the value of sigma d. Whether you are designing the gas system on based on the worm, or you're designing the gas system on based on the worm wheel. On which you are designing your gas system. Worm wheel, right? So you have to have the parameters of worm wheel. For example, sigma d of a worm wheel. Do I have that? Do I have sigma d of a worm wheel? Yes. Next, B. Face weight do I have? Capital Y do I have? And do I have the value of the module? Just here it is on the screen. Module is 8 mm. So just substitute everything. Okay. 52 is your design stress, which is specified in the problem clearly in the problem statement. 50 is your face width, just we have calculated. And Y is pi times of 0.1, and module you have just arrived at 8. So just calculate your dynamic tooth load based on the equation number 12.54 and give me the value of in terms of newtons. Okay, so both of them have given the value as how much? 653.41. So if you get the same value, please raise your hands. Let me see. Good, good, very good, very good. Good. So I can just approximately write it as in terms of kilonewtons as 6.53 kilonewtons. Okay, we shall look after it whenever it is required. Suppose if it is required in newtons, we'll substitute in newtons, or else in kilonewtons if it is required, then we'll substitute in kilonewtons. Now, limiting dynamic load or tooth load is done. We have calculated it. Now, what is our next step? Next step is to calculate the wear load. So, in order to calculate the wear tooth load, again, go to your data handbook. Please have a check in your data handbook. Is there any equation? Is there any data given through which in the worm gear segment I'm talking about to calculate the wear tooth load in the worm gear segment? Is there anything which is specified to calculate our wear tooth load? Please have a check in your data handbook and let me know. 12.62A. What is the page number, Dhanush?
227.
227. So it is, or 224 it is, 225, 226 and 227. What was the equation number? Here it is. The limiting load for wear. So he has given as D2BK, which is equation number 12.62A as specified by the Dhanush. Yes, you can take this. So take this particular equation for limiting wear load. Pick that particular equation. So if you observe the equations of an helical gear and a spur gear to calculate your dynamic tooth load or the wear load, they are very, very massive. They are very, very big in case of a helical gear and in case of a spur gear. But if you observe, in case of a worm gear, it is very, very small, isn't it? So it takes very minimal amount of time to calculate the thing. So just take that particular equation. So in that, the only unknown would be the value of K, isn't it? The load stress factor. So in the data handbook only, he has specified clearly. Just read it just below the data handbook what he has specified. K is known as a load stress factor, and it could be taken from the table number 12.330, that is 12.30. So can you just give me the page number through which I can refer my table number 12.30? Oh, here it is. I would get it directly. 12.29, 29, and 12.30. So this is your load stress factor for the worm gear for using an equation number 12.53d, which is this. Okay. Now, in this particular factor, on what basis should I select my value of K? That I have to decide, isn't it? So what is the value of our lead angle, by the way? Just we have calculated in this particular problem. What is the value of lead angle? It is 7.01, right? So there are three columns here. Column number 1, 2, and 3. So column number 1, you have to refer for 0 to 10 degree lead angles. And column number 2, you have to refer for 10 to 25 degree lead angles. And column number 3, you have to refer for lead angles which are greater than 25. Now, since your value in this particular problem is 7.02 and it comes in between 0 to 10 degrees, so we have to refer in this particular column. Very good. Now, in the particular problem, in the problem statement, has he specified any kind of materials for a worm and a gear? Gear is nothing but a worm wheel. You can worm wheel. Yes, he has specified. What are the materials for the worm and worm wheel he has specified in the problem? Worm is made up of and worm wheel is made up of. Which kind of materials? As indicated by the problem statement, hardened steel. This is for which one, Nitesh? This is for which one? Worm. So worm is made up of hardened steel. Very good. Next, what is worm wheel made up of? Bronze. Which bronze? Phosphorus bronze or antimony bronze? Which bronze? Phosphorus. Okay. Phosphorus bronze. Okay, so these are the materials. For these particular materials and for the value of gamma equal to 7.02, which is lead angle, what is the value of K you are going to obtain? Just look this hardened steel combination and phosphorus bronze combination. So this is the combination you have to look for. And your value of 7.02 lies in between 0 to 10 degrees. So come closer to here and your value of K is how much? 0.549. Correct? Any doubts in taking this particular value? Load stress factor. Any doubts? If you have any doubts, let me know. Okay. So pick up that particular value, write it down in your notes and clearly specify from which table, which page number you have taken that particular value of load stress factor for gamma equal to 7.2. That only validates your answer. Okay. You should not choose any value randomly. Okay. So K is equals to 0.549 is the value. Just substitute. D2 is 295 cross face resistor T, and the value of K is 0.549 from the table 12.3. Now, what is the value? What is the value? 809, 8097, 8097.85. So this is the value of wear load that you have obtained. That's a good thing. Now, can anyone draw the inference while comparing the value of dynamic load and the wear load? Anyone? Can anyone draw the inference? What conclusion can you get by looking at the values of wear load, by comparing the values of wear load and dynamic load? The same thing, the concepts remain same for all the gas systems, irrespective of whether it is spur, helical, or bevel or what. The concepts remains the same thing. So what inference could you draw by comparing the values of dynamic load and the wear load? Anyone? Just compare the values of dynamic load and the wear load. By comparing these two, what conclusions can you come upon? Yes, Sumit? Sumit, yes.
Sure.
So what conclusion?
Wear load is greater than.
Yes, the wear load is greater than the dynamic load. So that is the conclusion. So what the inference could you draw when the wear load is greater than the dynamic load? What happens when the wear load is greater than the dynamic load?
Hello.
Yes, Sumit.
Pressure.
Mohammed Saad.
Yes, sir.
So what inference could you draw by comparing the values of wear load and the dynamic load?
Not safe.
It is safe or it is not safe? So which one
Not
should
safe.
be good? Not safe. Very good. Very good. Excellent. Sumit Radvik, ಈಗ ನನಗೆ ಆನ್ಸರ್ ಮಾಡಿ ಡೈನಮಿಕ್ ಲೋಡ್ ಕಮ್ಮಿ ಇರಬೇಕಾ ವೇರ್ ಲೋಡ್ ಕಮ್ಮಿ ಇರಬೇಕಾ? So when you have a confusion, whenever there is a confusion,
Wear load.
wear load ಕಮ್ಮಿ ಇರಬೇಕಾ? How many of you would agree with this answer? Just give me in the chat box. So which one has to be the lower value? Whether the dynamic load has to be a lower value or whether the wear load has to be a lower value? Just everyone, I require answer from everyone in this class in the chat box. Right? Okay, now Sumit. So everyone is saying that dynamic load should be of a lower value. Now, what inference could you draw? Whether the system is safe or whether the system is not safe? Sumit.
Safe.
System is safe, isn't it? Convinced, Radvik?
Yes.
Okay. So always when you have a confusion, so always remember the dynamic load should be of a minimal value, whatever the other loads are, irrespective of the loads. For example, if you take wear load, if you take endurance load, if you take fatigue load, if you take heat load, thermal load, apart from all the loads, the dynamic load should be of a minimal value. So if your wear load is greater than the dynamic load, so automatically you can write a conclusive satisfactory statement stating that since the wear load is greater than the dynamic load, the material is safe against the wear. Just write that particular thing in your notes. I said you, whenever you have a confusion, remember the dynamic load should be of a minimal value. ಕಮ್ಮಿ ಇರುವಂಥದ್ದು ಯಾವುದು? ಡೈನಮಿಕ್ ಲೋಡ್. ಯಾವಾಗಲೂ ಡೈನಮಿಕ್ ಲೋಡ್ ಕಮ್ಮಿ ಇರಬೇಕು. Right. Next, you need to find the efficiency now. Okay. Next part is to find the efficiency. Now again, refer your data handbook. Check for the suitable equations, compatible equations through which I can calculate my efficiency. Did you find any equations through which I can calculate my efficiency? Please have a check. Equation number 12.57, 225 again, okay. 12.57. Okay, here it is, right? Efficiency of the worm gearing. Okay. Has it given us the value of mu? Is there any mu specified in the problem? No. Good. So we'll find out that. We have equations again in the data handbook through which you can find out the value of mu. Don't worry about it. No. See, how many equations are there to calculate your efficiency? Just check. Here is one particular equation, right? So there is one equation here. The second one is here. And the third one is here, right? So there are how many? Totally, there are 3 equations to calculate your efficiency, right? Now, which one to choose? Should I go with this particular equation? Or should I go with this one? Or should I go with the Bayes formula which I have used in the last one? Which one should I go with? Any idea? So let me explain you this. The first thing, you have to know how these equations are obtained. Number one, the Bayes formula, whichever it's there, eta is equals to, that is, efficiency is equals to tan of gamma minus into 1 minus mu into tan of gamma divided by mu plus tan gamma. So this particular equation is there, no? This particular equation is the arbitrary equation. Okay, that is empirical relation. It is not theoretically derived, but it is arbitrarily obtained. So it is always a least effective one or least accurate one. Okay. So, and one more thing is, this particular equation is not problem specific. Problem specific in the sense, just you require the value of gamma and you require the value of mu. You will get the efficiency. That's it. That means irrespective of whether it is a straight worm gear or a tilted worm gear, the efficiency equation remains the same thing. But when you observe the first 2 equations, there you have the value of theta in between. Okay, you have the value of theta in between. So what is this theta? Theta is the angle between the worm and the worm gear. Okay, so if that is taken care of, then definitely whatever the value of efficiency you obtain would be of a higher accuracy. So that's why always prefer the first 2 equations in the least possible case, if you don't have any of the data, then you can go with the Bus formula, as we have done in the previous problem, where it was a simple problem to get to know the parameters. Isn't it? Since this is a design-oriented problem, which is the problem number 2, always go with the first 2 formulas. Okay, now I said you have to go with the first 2 formulas. Very good. So which one to choose? Whether to choose the first one or to choose the second one. So the first one you have to choose. Clearly, he has specified that when the worm is driving the worm wheel, when the worm is driving the worm wheel, then you have to go with the equation, this particular equation number 12.57b. On the other hand, if the worm wheel is driving the worm, which is very rare case, always what happens, your worm will be driving the worm wheel. In a very, very rare case, your worm wheel will be rotating the worm. It is very, very rare. So if in such case, you have to go with this particular equation. 90% of the cases, what it would be, your worm would be driving the worm wheel. So pick this particular equation. Okay. So same thing I have done. Any doubts in this? Any doubts? When to choose what? Any doubts if you have, please let me know now, or else we will continue with the problem. Any doubts? So we are going with the equation number 12.57b. Okay. Just pick that particular equation, which I have done here. 12.57b. It is from the page number 225. Just write the equations. What are the different unknowns in this? We need to calculate theta. We need to calculate the value of mu. So these 2 parameters we need to calculate. Then only you are in a position to calculate the efficiency. Okay. First, we will calculate the theta. To calculate the theta, I will help you out. Go for the equation number 12.56d, page number 224. 12.56d, page number 224. In that particular equation, you have tan theta is equals to tan alpha into cos gamma. Okay, tan theta is equals to what? Tan alpha into cos gamma. You have that particular equation in page number 224. Pick up that. You know the value of alpha, which is the pressure angle, 14.5. And you know the value of lead angle, which is calculated 7.02. Substitute it. Make it tan inverse, then you'll get the value of theta. Please give me the value of theta. Did you get this particular equation? 12.56d, page number 224, to calculate the value of theta. Okay, good. 14.39. Shall I go with the value? Many are giving the same value. So it is 14.39 degrees. 14.39 degrees. Very good. Now, what is the one last parameter which is left out in order to calculate the efficiency? Mu. So you have just calculated the value of theta. Next, you are supposed to calculate the value of mu. Lead angle, anyhow, you know it, right? Now, all of you just observe, just stop working. If you are working on your notes, just stop working and observe here. Okay, this is very important. The calculation of mu requires certain concepts for it. So please do focus now. Stop working or stop calculating if you are calculating the things. Now, first thing, the value of mu will always depend on the rubbing velocity v to the suffix r. The value of mu would always depend on the rubbing velocity, V to the suffix R. V is nothing but the coefficient of friction, isn't it? It will definitely depend on the rubbing velocity. Now, where will you get this rubbing velocity? All of you go with equation number 12.6, which is in the page number 226. And can you find this particular equation where it says pi d1 small n1 divided by 1000 into cos lead angle? Just check whether you can find this particular equation over there. 12.6, page number 226. From there, you can pick up the value of rubbing velocity. So just substitute all the things. So pi into 65 cross 20 divided by 1000 into cos of lead angle is 7.02. Just substitute the things up and give me the value of VR. So once you calculate the VR, again you have multiple calculations to arrive at the value of mu. Okay. So first we calculate the VR. Let us see. So what is the value of VR, guys? 4.11. 4.11 meters per second. 4.11. Very good. Now, immediately you calculate the value of rubbing velocity is VR, whereas the linear velocity of the worm wheel or a worm is V. That is given by pi d1 n1 divided by 1000. So d1 is 65 and n1 is 20. You have calculated, and give me the value of V, which is the linear velocity. I have to compare the values of rubbing velocity and linear velocity. 4.08. Okay. 4.08. Now, all of you go with page number 226. So, page number 226. Okay. Okay, where are it? Okay. Here it is. Are you able to find this? Page number 226, you have the formulas to calculate the values of coefficient of friction. Here, 12.60A, 12.60B. You have two different formulas. This is the first formula and this is the second formula. Into VR is there. Okay. Now, how would you come at this particular formulas? Which one will you choose? You have to look for the velocity. Okay. So if the velocity is in between 0.2 and 2.75, you have to choose this particular formula, right? If the velocity is greater than 2.75, then you have to go with the second one. Now, should I go with 12.60A or should I go with 12.60B based on your value of V? So what was the value of V? V is 4.08. So should I go with which one? 12.6A or 12.6B? So as the value of 4.08 is greater than 2.75, then I would go with the value of formula 12.60B. Pick that particular formula there. Pick that particular formula, which is 12.60B, 226, and write it down in your notes. Down in your notes. Okay. Now, since you have calculated the value of the rubbing velocity, which is 4.11, do not get confused. This is just V, okay, and this is VR. This is the linear velocity, and this is the rubbing velocity. Rubbing velocity is given by 4.11 in this particular problem. You have to substitute the rubbing velocity here. Just substitute the rubbing velocity and give me the value of mu. So what is the rubbing velocity? It is 4.11. Okay, 0.038. Is the value same for everyone? 0.038. Okay. So once you have calculated the value of mu, you have calculated the value of theta, you know the value of gamma, substitute all the values in the equation there, in the above equation 12.57b, and give me the values of efficiency. So this is the whole into 100. Okay, this whole into 100. Give me the value of efficiency of this worm and worm wheel. %75%. So 75% is the efficiency of this worm and worm wheel. Okay. Now the problem is not yet done. So in the worm gear, you have to check for dynamic load, wear load. We have checked it. Next, you have to calculate the efficiency. At the last, after calculating the efficiency, at the last, you have to take care about the heat generated. So whether you have to suggest whether you require artificial cooling or not. Artificial cooling in the sense oil haktane irbeka. Okay, na? Whether should I keep a fan in the worm or worm wheel arrangement? What cooling system should I require? So all those calculations are there. So heat generated calculations we have to look upon. Okay, that is very simple. Don't worry about it. It's another 2 to 3 steps. Will complete the problem. Okay, so first we will calculate the heat generated. So heat generated is given by the equation Qg is equals to mu times of Fn into Vr divided by cos gamma, as given by the equation number 12.638, page number 227. All of you just look into the data handbook. Don't barely copy it from the screen. Look into the data handbook and pick the value from there. Okay, pick the equation from there. Okay, so it says mu into Fn into Vr divided by cos gamma. Fn is nothing but the normal load. It is not tangential nor radial. It is a normal load to the teeth profile. Fn is the normal load. And in order to calculate the normal load, I did not find any equation. I took it from the textbook. So we have to remember this particular equation, where through which you can calculate your value of Fn. Through which you can calculate your value of Fn. Okay, it says Fn is equals to Ft divided by cos gamma into cos alpha. Remember this particular equation. I have just highlighted in the notes also. Even you highlight in your notes. Okay. With that particular equation, try to calculate the value of heat generated. Sorry, I was speaking, but the mic was off. Okay, good. So you can find this particular equation in 12.63b, which is page number 227. Okay, so it says 1000 into kilowatt. Kilowatt is nothing but your power developed. Okay, power to be transmitted into 1 minus efficiency. Efficiency, I have just calculated the value. So just substitute all the values there. 1000 into 3.75 into 1 minus 0.7523, which is your efficiency value. And give me the value of heat dissipated. Okay, what is that value? 92. Okay, 928.8. 866. Mithun, just have a check. So it is 0.93 kilowatts. Now, all of you just observe this particular explanation concept. Suppose because of the worm and the worm wheel engagement, okay, continuous rubbing action will be there. Because of this rubbing action, think there is 10 kilowatts of heat is generated because of this heat, because of the rubbing action. 10 kilowatts of heat is generated. Now, because of the material property, if it is huge, it will be having a larger surface area of the worm and worm wheel. What it does, it starts dissipating the heat. It starts dissipating the heat to the atmosphere. And if this particular heat dissipation is 10 kilowatts, I have no problem. So 10 kilowatts was generated. 10 kilowatts of heat is generated, whereas the 10 kilowatts of heat is being dissipated. So 10 generated, 10 dissipated, no problem. Suppose if 10 kilowatts of heat is generated because of the rubbing action, and because of the material property, only how much? 8 kilowatts of heat is dissipated. Only 8 kilowatts of heat is dissipated. 10 kilowatts is produced, 8 is dissipated. Now, do I require the artificial cooling here? Do I require artificial cooling to compensate this difference? 10 kilowatts is generated. Heat is generated 10 kilowatts, but heat is dissipating only 8. ಹತ್ತು ಜನರೇಟ್ ಆಗ್ತಾ ಇದೆ ಕಣ್ರೋ, 10 ಜನರೇಟ್ ಆಗ್ತಾ ಇದೆ, ಅದರಲ್ಲಿ 8 ಮಾತ್ರ ಹೋಗ್ತಾ ಇದೆ, ಇನ್ನು 2 ಹಾಗೆ ಉಳಿಯುತ್ತೆ ಹೀಟ್. ಇನ್ನು 2 kilowatts of heat would be stayed in the system. For every second 2 kilowatts ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ, ಅಂದ್ರೆ ಹೀಟಿಂಗ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. Right? Do I require artificial cooling in such situation? Do I require or not? Definitely I do require, because your heat generated value is more and heat dissipated is less. 8 kilowatts, 10 kilowatt heat generate ಆಗ್ತದೆ, ಬರೀ 8 kilowatt dissipate ಆಗ್ತದೆ. You require artificial cooling. Understood the concept? With this particular concept, now you try to analyze the values whatever you have obtained. So heat generated value is 0.8 kilowatts, whereas heat dissipated value is 0.93 now. Heat is generated only 0.8. Now heat dissipated is more, 0.93. Do you require artificial cooling or not? In this particular problem, same concept you analyze now. Heat generated is 0.8, but heat dissipated is more. ಹೊರಗಡೆ ಹೋಗ್ತಾ ಇರೋದೇ ಜಾಸ್ತಿ ಜನರೇಟ್ ಆಗೋದಕ್ಕಿಂತ ಜನರೇಟ್ ಆಗ್ತಿರೋದು ಸ್ವಲ್ಪ ಆಗ್ತಾ ಇದ್ರೆ ಡಿಸಿಪೇಟೆಡ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಇದೆ. Do you require artificial cooling in such situation?
No.
Definitely not, because automatically your system is dissipating more amount of heat rather than it is generating. If it is generating 10, it is dissipating more than that. It is generating 12, 13, 14, as in case of this particular problem. So, at last, just write this beautiful sentence and close the problem. Since the heat dissipated is greater than the heat generated, artificial cooling is not necessary. And here your problem of worm gearing ends. So in the worm gearing design problem, what you'll be doing, you'll be calculating the module. Okay, you'll be calculating the dynamic load, you'll be calculating the wear load, you'll be checking that. After that, you'll be calculating the efficiency. After that, you will be going with the heat calculations. Heat generated, heat dissipated, you'll calculate and compare those two values to know whether the artificial cooling is required or not. Understood in this problem? Any doubts? Any doubts? No. Okay. Now, all of you just take the screenshot of this. So this the last problem was of the example where the center distance was known, and next problem is of the example where center distance is unknown. Okay, here the center distance should be not be given. So how to do such kind of problems we will discuss in the next class. So please do take a screenshot and write down in your notes the problem statement. It would be very helpful for me to start the problem straight away from the next class. So all of you can mark your attendance in the Google Sheet and leave the class. Have a beautiful day ahead. Okay, thank you.
Sir, Radvik.
Radhika. Radhika.